Good morning, friends. Today I am going to explain you the velocity triangles for the force exerted by a jet on a moving unsymmetrical curved when the jet of a water strike the van tangentially at one of its end. That is nothing but the concept of velocity triangle. Okay. So first we will discuss how to construct a velocity triangle. Okay. Before that, in the previous session, we have solved or came to know the procedure of impact of jet of single vane, impact of jet of a series of vanes when it is fixed and when it is moving. Okay. So as this velocity of jet triangle consists of the nozzle and diameter of the pipe. Okay, let d be the diameter of the jet. So this jet is there, this diameter. Then A be the area of cross section of the jet of the pipe. Then V1, this V1 and V2 are the V1, V2 are the absolute velocities of the jet at an inlet and outlet respectively, and U1 and U2. This is at the inlet, it is U1, and this is at the outlet, it is U2, are the velocities of the vane, and alpha is here and beta is here. That 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 alpha and beta be the angle made by absolute velocities with horizontal at inlet, that is alpha, then at outlet, that is beta. That is also called as guide blades angle. Let VR1, that is here it is VR1 at the inlet and VR2 at the outlet are the relative velocities of the jet at inlet and outlet respectively, and let theta be the inlet of the angle made by the velocity VR1 and phi be the angle made by the velocity at the V2. Okay, that is angle made by respect relative velocities with help of horizontal at inlet, that is theta, and outlet, that is phi, that is called as vane angles. Okay. Then, since the vane is moving, jet will strike the van with a relative velocity Vr1 at inlet and Vr2 at outlet. If the vane is smooth, then there is no shock. The jet of water leaves the vane with the same velocity as that of a inlet. So, if the vane is smooth, so this is the curved vane is there. If it is smooth, then jet of the water will be velocity will be same as that of V R1 and VR2. Therefore, VR1 is equal to VR2, that is the velocity diagram V1 and U1. Okay. Now, let us go through the procedure how to construct the velocity triangle from this. Okay. So, this is the figure. Now I am going to tell you the procedure to find the or to draw the velocity triangle at inlet and outlet. So you can have a look over this figure, okay, which is having a curve and the jet of the water when they striking at the inlet velocity with the help of nozzle, and that will be leaving the outlet of the vane at the velocity 2, it is v2. So for the construction of the velocity triangle, okay, let select a point. So I am selecting this point A. Select a point A and draw a line AB. Okay, I am selecting point A and drawing a line AB. Then this line from A to B will be the point of the inlet of jet point. So it should touching this in inlet of that point B, that is A and B. So A is the initial point and B the final point of where it touches the inlet of the inlet of the jet. Okay, then draw a line AB equal to the absolute velocity, that is nothing but v1, that is I am taking this as v1, both in magnitude and direction to a scale. With respect, with help of scale, both in direction and magnitude you have to draw. Okay, next draw a AC. Okay, this is horizontal line AC. Draw AC that is equal to u1, that is equal to u, that is u1 is initial velocity to the same scale, whichever I took the scale, that same scale I have to take it. Okay, then join CV. Okay, so this will be coming at this point. So here I will get a one point at C, then B point is there, then I will join this point, and that is called point line of CV, which represent the relative density VR1. So this represents the relative density VR1 at an inlet. So this is the inlet. Produce AC. So this horizontal you produce in such a way that you will get a point D. Produce AC and drop a perpendicular from B. So here B point is there. Just I will draw a dotted line perpendicular to this. Okay, produce AC and draw a perpendicular line B to meet AC. So then call this as a point D. Okay, then this line BD will call it as VF1, that is the velocity component. V1 BD is also called as velocity flow at the inlet. This BD line is called velocity flow at inlet. So then this VR1 with inclined with horizontal will be theta, and AB line with inclined with the line AC or AD is called as alpha. Then this triangle ABD is known as the velocity triangle at inlet. So this is called as velocity triangle at inlet, and from distance from A to D is called as VW1. Okay. Similarly, now we'll go for velocity construction of the velocity triangle at outlet. So this will become the inlet and B point, and D point, that is outlet. So I am going to tell you the how to draw the triangle velocity triangle at outlet. Okay. Next, so similarly draw EF. So this line AB is there, so I will go for this line. Draw EF representing the absolute velocity, that is V2. Here it is V1 and this becomes a V2 at the outlet. Okay, draw FG. So this draw FG horizontal line representing the velocity of the vane at outlet, that is called as U2. Here it is U1 and it is called as U2. Okay, then that will be same as that of U1. So draw FG then here it is FG horizontal line which will be there tangentially to the outlet tip and will be equal to the magnitude of the direction of the relative velocity at outlet, that is VR2. Okay, I will join this line E and G, then become the VR2. Produce GF, this GF line, okay, up to H. Then draw a perpendicular line from this which touches the point at E to meet GF and H at the point of the outlet line, that is called as FH, that is VWR. Okay, therefore the horizontal component V2 is GH, which represents the velocity of the outlet VW2. This is VW2. Therefore the velocity component of V2 is EH, which represents the velocity flow at the outlet EH, velocity flow at the outlet VF2. So therefore triangle EGH represents the velocity of the triangle at outlet. Okay, then similarly we'll be having, if this is the case when beta is less than 90 and this is the case when beta is equal to 90. So beta, here it is the angle made by horizontal. So if it is equal to 90, then at the outlet V2 is equal to VF2, then this will be U2, then this will be R2. Similarly, if beta is greater than 90, then therefore here U2 will be from the line G into F, then this HF is equal to VW2. So this is the beta which is greater than 90, this is the 90 line. So if it is greater than, then the velocity of the triangle will be, so G, F and D. So similarly, three cases, when case 1 beta is less than 90, this will be the triangle. When beta is equal to 90, so this is the triangle. When beta is greater than 90, this will be the velocity triangle. So in the next session we will be discussing about the formulas related to this. Okay, thank you.